So you're expected to be familiar with the structures of groups up to an order of 7. Now that doesn't mean you need to know everything from memory about groups, but you should be able to infer certain things. Now when we're comparing the structure of two groups, these are the following things that we need to be thinking about. So the order of the groups, okay, so how many elements are in the group, okay, because if you've got a different number of elements, that's one valid comparison, or if you've got the same number of elements, that's a valid comparison as well. Then the orders of the individual elements, especially if you have a group of the same order, or let's investigate the orders, how many self-inverse elements, for example, does one group have, and compare it to the other one, and so on. Then is the group cyclic or not? So if one's cyclic and one's not cyclic, that's a clear comparison to make. And the same with regards to whether they are abelian or not. Okay, that's another thing to be thinking about. So if it's cyclic, then it has to be abelian. Otherwise, you should be looking at the Cayley table and seeing if it's symmetric. Now let's go through some of the orders up from 1 up to 7. Now in the last video, we already looked at groups of order 4, so I'm not going to talk about them again. Now, let's say we have a group of order 1. Well, this is a fairly boring group. Okay, it's a trivial group. It's just the identity on its own. Okay, because clearly there's a unique identity in the set. The identity is self-inverse. Okay, if you combine the identity with itself, it's going to be associative for all sort of combinations. So all axioms are logically satisfied. Okay, it's definitely going to be closed. Identity combined with identity is the identity. There's not really too much to talk about there. Now, let's say we have groups of the same prime order. So multiple groups of order 2, or order 3, or order 5, or order 7, if we're going up to 7. Well, there's certain things we can infer here. All prime order groups are cyclic. The reason being, the element orders are going to be a factor of the group order. So if I pick one of these, for example, for 3, our possible element orders are 1 or 3. Okay, and similar would apply for 5, 7, and 2. Now, an element of order 1 is the identity, and that's reserved for the identity only. Therefore, all other elements must have an order of 3. Okay, and therefore all the other elements are generators, and therefore this is going to be a cyclic group. So in your prime order group, all non-identity elements will be generators. Therefore, also, if it's cyclic, we can definitely say they're abelian. And if you take any two groups of the same prime order, they are going to be isomorphic to each other. They will be identical because all of the element orders are going to match. They're all going to be equal to the group order apart from the identity. So you will have identical groups. Also, thinking about subgroups, our possible subgroup orders are the same as the element orders. Okay, so it'd be 1 and 3 for 3. And they would only be our improper subgroups. Okay, so there are no proper subgroups for our groups of prime order. So you should be able to infer that using your definitions of certain things relating to groups. Now, the other number we haven't considered yet is an order of 6. Now, just like an order of 4, there are only 2 possible groups you can get for an order of 6. Now, just like the order of 4 that we did in the previous video, I would suggest that you try and go through and list out all the key information. Okay, find all the orders, find all the inverses, the subgroups, whether it's abelian, whether it's cyclic, or so on. I'll leave that as a task for you. So just a reminder, we don't necessarily need to memorize things about groups of order 4 and groups of order 6, but you should be able to logically figure these bits of information out